Okay, so here we are again with some quantitative chemistry, looking at the mole and the Avogadro constant. You have a sheet based on that, and that sheet's really based all about moles and mass relationships. Okay, if you've got mass of a substance and you want to know how many moles you've got, or if you've got moles of substance and you want to know what the mass is. Well, for that we're going to use this formula. The number of moles is equal to the mass divided by the molar mass. Now, important things to remember, and remember this from the exercise you did about finding out the number of grains of sand and equating that to the number of moles. Well, the most important thing to remember is that moles are just particles. It's just a number. Okay, it's just an amount of substance. If we're ever asked to find an amount of something in chemistry, we want to know how many moles we've got. How many moles we've got. We use the symbol lowercase n when we're referring to moles, and it's just a number, and it's nearly always going to be a number of particles. We have to decide what those particles are. Mass in that formula will always be measured in grams. If it's not in grams, you're going to need to convert it to grams. And molar mass has the symbol capital M and has units grams per mole. So if you think about what's going on, if you're dividing mass, which is in grams, and you're dividing that by grams per mole, the grams cancel, you're left with 1 over per mole, which gives you moles. Now, molar mass, how do we find molar mass? Well, molar mass, quite simply, we take from our periodic table. And if we're looking at an element, we're talking about an element, then the molar mass will just be the relative atomic mass, or the AR, capital A, subscript R, and we find that from the largest value for each element on our periodic table. If it's a compound, well, we're talking about the relative molecular mass, or the MR, capital M, lowercase r, of the compound, and we just find that out by adding up all the relative atomic masses of the elements in the compound. And we find all those values from our periodic table. Now, relative atomic mass and relative molecular mass do not have units, but they're just the same value, the same number as the molar mass. Okay, let's take some examples. I've put a bunch of questions up here which come from your sheet. If we have a look at those together, the first thing's asking us how many moles of substance are in the following. And you can see in all the cases we've given masses. Okay, we're not given volumes of solutions, we're not given volumes of gases, we're giving masses of substances in grams or kilograms. Well, if we want to find out how many moles there are in 72 grams of magnesium, well, if you look at your periodic table, I hope you've got one out in front of you. Pause now and go and get one. Okay, welcome back. The relative atomic mass of magnesium, we'll see, is 24. Okay, AR is equal to 24. So, the mass of magnesium is 72 grams. Divide it by the molar mass, 24, and we get 3 moles of our magnesium. You'll notice that I've just shortened moles to MOL. That's our unit for moles. Next, we're trying to find out the number of moles we have in 39 grams of aluminium hydroxide, which is aluminium hydroxide. If you look at your periodic table, you'll find that aluminium has a relative atomic mass of 27, hydrogen 1 and oxygen 16. So in that case, the relative molecular mass of aluminium hydroxide is 27 plus 16 plus 1, all multiplied by 3, which gives us 78. So our number of moles is the mass, 39, divided by our molar mass, 78, which gives us 0.5 moles. Copper oxide. Copper, from your periodic table, has a relative atomic mass of 64, whereas oxygen is 16. So our relative molecular mass is equal to 80. 4 kilograms. Well, 4 kilograms, of course, is equal to 4,000 grams. So the number of moles of copper oxide we have, 4,000 grams, divided by the relative molecular mass, or the molar mass of 80, which gives us 50 moles. Okay, now what happens if we want to work out the mass of a substance if we're given the number of moles? Well, we're just going to use our formula, the one we've shown already, number of moles is equal to the mass over the molar mass. Of course, if we rearrange that, we find that the mass is equal to the number of moles multiplied by the molar mass. Chlorine, a diatomic gas. Remember Mr. Brinkelhoff? Diatomic gas, so its MR is 5.5 times 2, which is equal to 71. So the number of moles the mass we have will be equal to 5 multiplied by 71 is equal to 355 grams. Ammonium sulfate over here. Work that out. Pause. Okay, you've found it out. It's got a relative molecular mass of 132. So the mass of 0.002 moles comes out to be 0.264 grams. Okay, moving on. Here's an interesting question. Question about Buckminster fullerene. That football-shaped molecule. It's a little bit lopsided there. It should be spherical. But anyway, I'm told here that I've got 3.6 grams of Buckminster fullerene. Carbon, if you look at your periodic table, carbon has a relative atomic mass of 12. So the relative molecular mass of Buckminster fullerene is 12 times 60, which is 720. So if we want to work out the number of moles of molecules of Buckminster fullerene, it's equal to 3.6 divided by 720, which is 0.005 moles. Now, how many atoms of Buckminster fullerene do we have? If we've got 0.005 molecules, 0.005 moles of molecules, then if we want to know the number of moles of atoms, we multiply how many molecules we've got 0.005 moles of them, but we would want to multiply that by the number of atoms in the molecule, 60. So I've got 0.3 moles of atoms. Now what about if we want to know how many actual molecules and how many actual atoms we've got? Well, we remember we've got the Avogadro constant, being equal to 6.02 times 10 to the power of 23. So, in 3.6 grams of Buckminster fullerene, the number, if you like, of molecules would be equal to 0.005 multiplied by 6.02 times 10 to the power of 23, and the number of atoms we've got would be equal to 0.3 times 6.02 times 10 to the power of 23. Giving me 3.01 times 10 to the power of 21 molecules, or 1.806 times 10 to the power of 23 atoms of carbon. Okay, thank you. Any problems? Come see Mr. Good.